Beamer full screen.
Okay.
Yeah.
Hello for all. The title of this talk is...
No, just wait. Maybe I should introduce you to you first of all. Again, all of you are welcome to Monday afternoon session. And my best wishes from Ankara, Turkey. Today afternoon session, we have 3 talks, and the first 2 talks are 20 minutes, and we have 10 minutes for questions and discussion. And the last talk is 30 minutes. Our first speaker, Professor Nasri from Tunis Al Manar University, and his talk title is The Sup-completion of a Dedekind Complete Space. Professor Nasri, welcome. You can start.
Okay. Hello for all. The sup-completion of the Dedekind complete space is the title of this talk. X is the Dedekind complete space. XU is the universal completion of X. XS is the subcompletion of X. The notion of subcompletion has been introduced by Donner. XS is a lattice code which contains X. XS has the following property. For example, P1 X is P1 X is the set of invertible elements in XS. Also, P4 if X an element of X and Y an element of XS satisfy Y less or equal than X, then Y an element of X. Also, XS has a greatest element. We have also the property P8 if A and B are not empty subset of X, then the supremum of A plus B is equal the supremum of A plus sub B, supremum of B. We have also the extension of Birkhoff inequality on XS. Also, there is the composition property on XS plus extension of maps theorem. If let X and Y be 2 Dedekind complete space and a map F from X to Y be an order continuous increasing map, we have the following property. The first, F can be extended to unique left order continuous increasing map Fs from XS to Y to YS. Moreover, if F is additive, respectively positively homogeneous, then so is Fs. We have also the property if F from X to X is strictly positive order continuous linear projection, and Fx, the range of F is a regular subspace of X, then the range of F is regular and the range of the extension of F is equal the subcompletion of the range of F. We have also the property for if F is in addition linear and Z is a regular real subspace of X, which is invariant under F, then the sup-completion of Z is invariant under Fs. We have the corollary, the following corollary. Let T be a conditional expectation operator defined on the Dedekind complete real space X and fixing an order weak unit E, then the range of T is a regular real subspace of X, and the range of the extension of T is equal the range, the sup-completion of the range of T. We have also the following the second corollary with the same notation come above. If G is in the sup-completion of the range of T, then the range, the sup-completion of T is invariant under the band, the extension of the band projection generated by G, and the disjoint and the extension of the disjoint of the band projection generated by G, and the band, the sup-completion of the band generated by G and the disjoint of the band generated by G are invariant under the extension of T. Moreover, TS and PGS are commute, and PGDS and TS are commute also. We have also the following theorem. All space and the following statement are assumed to be Dedekind complete, and all maps are order continuous and increasing. If F, property 1, if F and G are two maps from X to Y, satisfy F less or equal than G, then the extension of F is also less or equal than GS. We have also if H is equal to F plus G, then the extension of H, the extension of the sum of F plus G are is equal the sup-completion is equal the extension of F plus the extension of G. We have also the composition. The extension of the composition of G and F is equal the composition of the extension of F and G. We have also there is the composition of property and XS. The sup-completion of A plus B is equal the sup-completion of the supremum of A plus B is equal the supremum of A plus supremum of B, where A, B are two subset of XS. We have also the sum property in XS plus. If X alpha and Y beta be two net in XS plus and X, Y are two elements in XS plus, such that X is the supremum of X alpha and Y is the supremum of Y beta of Y beta, then the following hold. X plus Y is equal the supremum of X alpha plus Y beta. the supremum of X and Y is equal to the supremum of X alpha and Y beta. And the infimum of X and Y is equal to the supremum of infimum of X alpha and Y and Y beta. We pass now au second part, finite and infinite parts. We have the following theorem. If X an element of X plus, then there is an unique projection bond B in XU such that X is equal the greatest element of bond B plus U with U is an element of the disjoint of the bond B. Definition of finite and infinite parts. Let X be an element of XS plus, then infinite B is the infinite part of X and U is its finite part. They will be denoted comme following. We defined the product of two elements in X and Y of XS plus come follow. And we have some property for the product in XS plus. For example, if B and C be two bonds in X and X and Y, two elements in XS plus, the product X and by the greatest element of XS is equal the greatest element of the bond generated by X. And the infimum of the greatest element of B and C is equal the product of the greatest element of B and C. And the supremum of the greatest element of B and C is equal the sum of the greatest element of B and C. We have also the finite part of X product Y is equal the product of the finite part. And the second, we assume that A is a Dedekind complete Riese space and E is a weak order unit in A, and T is a conditional expectation operator with TA equal A. We have the Borel-Contelli lemma. The first one, the first Borel-Contelli lemma has been generalized to the setting of the Riese space by Q, Labouchaine, and Watson. Here is a slight generalization. If Xn be an order bounded sequence of X, if the series is order convergent in XU, then the limit sub of Xn is null. We have also the second Borel-Contelli lemma. If Pn be a sequence of T-independent band projection in X, and if B is a band of XU such that this series is equal infinite b plus u, with u is in the disjoint band b, then pb commute with t, and pb is equal limit sup of pn. Application for Borel-Cantellier-Lemma. A criteria for your convergence or unbounded convergence. Theorem. Let xn be sequence in x, and let x an element of x. The first property if is the following. If for all epsilon strictly positive, such that the following series is order convergent in xu, then xn is IO convergent to x. The second property, if this series is order convergent in xu for some r strictly positive, then xn is IO convergent to x. And second application for the Borel-Cantellier lemma is the following theorem. If Tn be a filtration adapted with T, and if Xn Tn be a martingale in X satisfying the following property, the following relation, define the projection band in XU as follows. Then the disjoint of this band band projection Q is equal the band projection generated by the infinite part of the supremum of the sequence Xn. The last application is in the following theorem. Let Tm be a filtration adapted with T, and let Pn be a sequence of band projection satisfying Pn Tn equal to Tn Pn for each n. We have then the series of general term Pne and the series of general term Tn-1 Pne have the same infinite part. Thank you.
Thank you very much, Professor Nasri, for a nice talk. Are there any questions or comments? May I ask a question? For the Borel-Cantellier lemma, the second one, I guess in the 32nd or 33rd slide, you mentioned that the Pn should be T independent. Why do we need T independency for the sequence Pn?
T independent in the sense at T Pn Pm A is equal T Pn T Pm A is equal T Pm T Pn A for all n
For the sequence Pn.
for all n and m not equal. Not equal.
Okay, I see. Thank you very much. Any other question? Yeah.
Just to give a comment, it's a joint work, and you see that this theorem has not been obtained before the second Borel-Compte lemma, because the condition that the series is not convergent. It's not clear how to be interpreted in the case of Riesz space, because for real series, for positive real series, we have converging or diverging. And so here, the series may be converging on some bands. And then we take the greater band, the greatest band on its convergence. And so we introduce the notion of finite and infinite parts to describe this fact in a clear way. And I think that its notion of finite and infinite parts will allow to obtain very transparent generalization of many results, like the two last theorems, which that appeared in the book of Kendra. There is a book 10 years ago about Borel, many generalizations on Borel-Compte lemma.
Okay, thank you very much for the comments. Any other? If there is no more question or comments, we have 8 minutes for a break for the refreshment. We will start at 1 o'clock with Tunisian time. We have 8 minutes more.